We're going to talk about the Boeing 737 MAX 8 crashes. But why? Why are we talking about plane crashes at a mining conference? Well, the really interesting thing about when you look into failures and why failures happen, particularly within organizations, is that while we may have different technical causes of failure, the organizational reasons why things go wrong tend to be always very, very similar. So there's a lot of learnings we can take from one industry and bring them to another. And this is really about looking beyond the immediate causes of failure. And how do we find the endemic failures that sit inside our organizations? So we're going to talk about the Boeing. We're going to talk about a really crazy thing called the sand pile model. We'll even touch on the First World War in this, and you may have to bear with me on that one. There's a content warning. Obviously, we're going to be talking about plane crashes, so if anyone wants to duck out, totally understand that. And we start on the 29th of October 2018, Sakarya International Airport. And Lion Air 610 is preparing for departure. This is a Boeing 737 MAX 8, one of the relatively new Boeing planes out on the market. In control is Captain Suneja. He's 31 years of age. He's got 6,000 hours in the air, most of it in the predecessor to the MAX, the 737. Sitting beside him is the co-pilot. He goes by one name. He's called Harvino. He's a decade older. He's got about 5,000 hours in the air. So two very experienced pilots. 6:20 a.m. they depart from the airport. They take off, and the first moments of this flight are pretty normal. That's time along the bottom, and that's altitude of the aircraft in the green and the red. And then things start to go wrong, and they start to go wrong very, very quickly. So the central column, the controller that Suneja uses to control this aircraft, starts to vibrate in his hands. Now, when that central column starts vibrating, that's usually a precursor and a warning that you're about to stall the aircraft. What does stall the aircraft means? It means fundamentally that your angle gets too steep, your so-called angle of attack. If it gets too steep, you disturb the airflow over the wing, you lose your aerodynamic ability, you basically turn into a stone. If you don't get control of the plane again, you crash. So this is a stall warning, and it's serious, and it confuses Captain Suneja because they're nowhere near an angle where this should be happening. At the same time as that central column starts vibrating, two alarms go off in the cabin: bad altitude and airspeed. Harvino turns to Suneja and says, "What do you want to do? Do you want me to get a path back to the airport to land?" Suneja says, "No, I need to figure out what's wrong with the aircraft. Just give me a holding pattern." Harvino gets back onto the control tower. He says, "Flight control problem." And as this central column is vibrating in Suneja's hands, and as these warnings are blaring in the cabin, the plane does something very weird and quite terrifying. It suddenly pitches forward. And the pilots just see the blue water of Jakarta Bay out the window. For Suneja, there is no reason in the world why the plane would do this. He reaches down and he puts his thumb on this little switch here. This is called a trim switch. And what it does is when you hold it, it trims the horizontal stabilizer, the little wing on the back of the aircraft, to bring you back up level. And he holds that switch, and the nose of the plane comes back up to where it should be. He lets go of the switch. No sooner has he took his thumb off it when the plane suddenly pitches forward again. Sitting beside him, Harvino is going through their quick reference handbook. This is the handbook you go to if something really unusual happens in the plane. It'll tell you why it's happening, and it'll tell you what you need to do, the checklist to get out of trouble. As he goes through this quick reference handbook, he can find no reference whatsoever for why this plane should pitch forward. And therefore, he's got no guidance at all on how to rectify the problem. So the flight that started out nominal is now far from nominal. They were cleared for 27,000 feet. They have not got 5,000 feet above the ground. And just have a look at that trace to see what the altitude of that plane is doing. Over a period of 8 minutes, when Suneja fights with this plane, He holds that trim switch, it brings the nose back up, he lets go of that trim switch, that plane pitches forward again. It does that 21 times over that 8-minute period, and they do not get above 5,000 feet. Suneja asks Harvina to take over control. He probably wants to have a look at the quick reference handbook himself, or at least get time to think. Harvino takes over control. No sooner has he taken over control, where the plane pitches forward and he goes, whoa. He reaches out, he grabs the trim switch, he presses it, but he doesn't hold it for as long as Suneja held it. And the plane pitches forward again. At this stage, sync rate is blaring in the cabin, and they're almost flying vertically downwards. It is just blue water and rapidly approaching blue water. Terrain starts blaring out over the intercom in the cabin. When they hit the water, they're traveling at over 500 miles per hour. Everyone on board is killed. 189 people. Now, in the days that follow, two narratives start coming out. One of them is driven by Boeing, by the CEO, by the chief engineers. It's even driven by the FAA, the regulator in the US. And the narrative is the plane is fine. There is no problem with the Boeing 737 MAX 8. The problem, and this was steeped in racism, was a badly run Asian airline. This wouldn't have happened in the US. They said the problem was this pilot and the maintenance crew on the ground. But while that was the public narrative, behind the scenes, both in Boeing and in both the pilot community, a different story started to come to light. One of them was this word, MCAS, kept coming up again and again and again. What was MCAS? And the early reports from the incident were really disturbing. There's two sensors on the front of this plane called the angle of attack sensor, and it does exactly what it sounds like it should do. It measures that angle of attack so that the pilots know whether they're approaching a stall. And the word is coming out from the investigation that one of those sensors on Lion Air 610 had a mechanical or an electrical problem. There was something wrong with it. But that made no sense. How on earth could one sensor crash a plane? You know, the sort of the history of aviation is really the history of building redundancy into our aircraft. How do we get to a situation where a single point failure can crash a plane? How does that actually happen? Well, to try and get our head around this, we have to really try and understand how we as human beings think about cause and effect, because we've got a really funny relationship with cause and effect. We love to believe that there's a direct relationship between cause and effect, and we love to believe it's proportional. So in other words, if we see a really bad effect, we say, well, that must have had a really bad cause, and we go looking for that smoking gun. But what we find in a lot of failures is that you don't have a big smoking gun. You don't have that at all. You have lots of little things that seem to come together to produce a failure, regardless of what industry you're in. And how does that happen? Because that sort of breaks how we think about failure. And probably the biggest disconnect, one of my favorite examples of a disconnect between cause and effect, is the First World War. You know, in terms of an effect, the First World War was truly horrific. You know, millions dead, Europe scarred for a long time, the map literally redrawn in Europe. But what had caused this massive effect? Well, it was the assassination of one man that caused it. It was in Sarajevo, 1914. A Serbian nationalist by the name of Gavrilo Princip jumped out of the crowd with a gun, shot this man, the heir to the Austro-Hungarian Empire, very big empire at the time, killed him. That was what started or caused the First World War. But how could the assassination of one person, even someone that important, result in Europe tearing itself apart? How do we explain these sorts of failures? How do we explain how one sensor can crash a plane in the modern era? And to do that, we have to really go and look at how we think about systems. And most of us think in terms of simple systems, and we'll talk about what that is in a second. But in reality, when we look at these failures, we're looking at what's called complex systems. So what's simple systems? Well, simple systems are systems that we engineers tend to be really familiar with, and they fit with how we're trained. And to understand a simple system, what we're trained to do is break that system down into its components. And when we understand how each of those components work, we can put them back together again and we know how the system works. Many of the engineering systems we try and design, we design them just like that. But complex systems are different. They don't follow the rules like that. And the reason why is we can say that simple systems are the sum of their parts. But in complex systems, the interactions between those parts almost become more important than the parts themselves. And this is really difficult for us, particularly for engineers, because we're never trained to look at the interactions. We assume the interactions are just there, but interactions are strange and they do unusual things. And it's the interactions that produce the complex behavior. So while we say the simple systems are the sum of their parts, when it comes to complex systems, we have to say they're the sum of their parts plus their interactions. And there's a really intuitive example of a good complex system, and that was a sports team. We all intuitively know that a sports team is much more than the sum total of the talents of the individual players. That if you get a group of players who are really good and they interact with each other in the right way, you get a type of magic from a team. You can have a team of mediocre players who will play much better than a team of stars. And that's because of the interactions. And a lot of the systems that we deal with in life are these type of complex systems where these interactions really matter. And it's these interactions that cause this disconnect between cause and effect. This is why we have failures. Many of the failures we deal with in industry, many of the fatalities we deal with, there's this disconnect between cause and effect. Simple causes producing big effects. One sensor can crash a plane. So how do we think about failures like this? So we need a different way to think about how these failures happen within our organizations. And perhaps the best example of this is something that's a little bit crazy. And it's called the sand pile model. Now this was developed by a group of physicists. And it's one of these things different way. And what Perback, who was the physicist who put this together, said, imagine we have a table and we can honestly do 2 weeks course on sand piles and how this all works. But imagine we have a table and we're dropping 1 grain of sand at a time on that table. And we're dropping the grains of sand, they're all identical, at random places on the table. We don't know where the next one's going to fall. And as we do that and time passes, it's going to be pretty boring. But then over time, we're going to start forming little hills. And those little hills are going to get bigger and bigger and bigger. And where those hills form, we don't know because it's a function of where we're randomly dropping the sand. And then eventually what's going to happen is one of those hills is going to get so steep that we're going to drop a grain of sand, it's going to hit that hill, and we're going to get an avalanche. Avalanche of sand grains. Now that could be a small avalanche, it could be a big avalanche, it could be an avalanche that hits another hill and causes a further avalanche there. So we could get cascading failures. And what Perback asked us to do, he said, what causes the avalanche? We've got this system of sand, what causes the avalanche? And intuitively, most of us say, well, it's got to be the grain of sand. I mean, if we hadn't dropped the grain of sand, we never would have actually had the avalanche. That's got to be the cause. But he says, hang on a minute, you need to think about that a little bit more. For a start, you've been dropping grains of sand all day, and they haven't caused an avalanche, yet this one did. What's different about this grain of sand? And the answer is nothing. Secondly, even when a grain of sand causes an avalanche, we don't know whether that's going to be a big avalanche, a small avalanche, or multiple avalanches. So the consequence, the flow from this, cannot be explained by just a single grain of sand itself. And what Perback said to us is, it's not the grain of sand. The grain of sand is merely what initiated the avalanche. What caused the avalanche was the shape of the hill. It's the shape of the hill that matters if we want to understand avalanches and we want to understand failures in systems. The shape of the hill is critical because what it did was it created a situation where all it took was 1 grain of sand to cause an avalanche. But everything we do in engineering, in how we manage risk, is about managing the grains of sand It's not about managing the shape of the hill. And Peerbach says there's this concept of a critical state. What we do with all our systems is we wind them up so they actually tend towards failure. So if you think about it, every grain of sand we drop on this table that doesn't cause an avalanche actually increases the probability of an avalanche in the future, because we've just made another hill a little bit steeper. And what we're sort of trained whenever we look at failures and investigations and all these things, we're trained to go look and find the grain of sand that if it hadn't fallen, we would never have had the avalanche. Go and find the initiating event, and we usually blame it. And we can see this in most of the failure investigations we do. BP, Texas City, 23rd of March 2005, massive explosion on site. This is the Chemical Safety Board video. You basically have hydrocarbons starting to escape from a blowdown drum on site. People start to see this. Have a look in the bottom left-hand corner. You'll see some buildings. They're temporary buildings. They should never have been there. So those buildings on the left, particularly the big one, they were well inside a zone for temporary structures. And look at how the hydrocarbon cloud just disperses over the site. You have a vehicle. Again, it shouldn't have been there. It's running. Two people in the vehicle. They try to switch it off, but it actually starts pulling in the fumes and running faster. They escape from the vehicle, try to make an escape from it, and eventually you get a backfire and an ignition source, and it rips through the plant. And it destroys all those temporary buildings where people were in meetings. 15 people killed. One of the worst disasters in the US. And what's interesting is you can talk about the technical cause of failure and why we had hydrocarbons escaping from the blowdown drum. But when you actually try and take a sand pile model and a complex systems view of this failure, what you find is that the seeds for this have been sown a long time before. But the company had gone through 10 years of let's just cut costs, cut costs, cut costs, cut costs, cut costs, cut cost. They built this hill of cost cutting inside their organization where all it took was a simple technical failure to result in a catastrophic disaster. We see this again and again and again. One you'd be very, very familiar with. Pike River, November 2010, 29 people killed underground. What was the sand pile they built inside their organization? Well, they had a plan for mining, and that plan went wrong very, very quickly. And they had huge number of gas exceedances from the very beginning inside this mine. And they built this massive sand pile of gas exceedances that just sit there waiting for the spark, just waiting for that ignition source that will give you the explosion on that particular day. And the really interesting thing, particularly in mining, is we're not good at spotting these hills inside our organization, these hills that are just waiting for that one grain of sand to hit it. And one of the primary reasons why we're not good at this is all we care about when it comes to safety is this sort of rubbish. All we're doing is counting grains of sand. That's all we're doing here. We're not looking at the hill at all when we focus on these personal safety metrics like the TRIFR and the LTIFR. And the crazy thing is that the more senior people you talk to, they genuinely believe in mining that by making that TRIFR go lower, they are making their sites safer. Meanwhile, they're ignoring their catastrophic and their fatal risk hills that they're building inside their organizations. Because the causes of the incidents that end up in these metrics are not the same causes of the catastrophic and the fatal accidents. If Qantas told you they were managing the risk of a plane crash by focusing on reducing the slips, trips and falls of their baggage handlers, we'd laugh at them. And we do that in mining every day in Australia. And that's going to get worse because that's now found its way into the ESG metrics. So now all boards will care about is my TRIFR going down? Is my LTIFR going down? And what you found with Pike River was that they were focused on those numbers as well. Meanwhile, they were getting evidence that their systems weren't working, the critical controls weren't working, that the number of gas exceedances that they were getting were going up and up and up and up and up, and the board wasn't looking at anything like that. That wasn't featuring in their decision making, so they couldn't see the hills of sand that were just waiting for those grains of sand to fall. And there's no better example of this than Deepwater Horizon. In April 2010, there's a group of executives flying to the Deepwater Horizon rig to give a safety award. Because this rig has just gone 7 years with no LTIs. 7 years. 125 people on this rig at any one time. And in 7 years, they never had a single LTI. The reality is, of course they did. They had lots of safety problems. But when you focus on personal safety metrics and you as a company want them to go down, they will go down, particularly if you're using contractors. They'll go down really, really quick. You'll be told what you want to hear. Meanwhile, you miss the rest of the sand piles that are sitting in your organization. So with all of that, let's have a look at Boeing. Let's look at the sand pile Boeing built, where all it took was one sensor to crash a plane. So Boeing starts off early 1900s. They really grow after the war. By the 60s, they've got about 140,000 employees. And they're an interesting company because their entire focus is on the engineering. Get the engineering right. If you get the engineering right, you'll have reliable planes, you'll have safe planes. And you know what? If we do that, we'll make money. That was the entire focus. They even had a mantra inside Boeing, which was, we hire engineers and other people. But by 1997, they took over McDonnell Douglas, a rival airline company. Very different company in terms of culture. For them, engineering wasn't first. Cost cutting and return on shareholder investment was first. That was the entire focus. And when you have a company where that becomes the focus, people who are good at cost cutting and focusing on return on shareholder investment get to the top of that company. And then you take these two companies, one with a focus on engineering and one with cost cutting, and you mesh them together, and you say, we're going to have one culture. Which culture do you reckon wins in that situation? One Boeing person said it was like watching a group of hunter-killer assassins being let loose on a room full of engineers. Within 10 years, the bean counters had made it to the top, and engineering excellence had really gone down the line. The other people were firmly in charge within Boeing, and we start to build a sand pile. And with that background, they get blindsided. And they're blindsided by Airbus. So Airbus is their biggest rival, European consortium of aircraft manufacturers. And they come out with, in 2010, the A320neo. Now, the A320 had been around for a while. Really good aircraft. The neo was a game changer. And it was a game changer because it had incredibly fuel-efficient engines. And Boeing had nothing to compete with this. In what I think is a wonderful example of why you should never let us engineers do any marketing, NEO stands for New Engine Option. It's fantastic. So they come out with the Airbus, Boeing are blindsided, and the sole purpose of this aircraft is to compete with this one, the Boeing 737. Been around for a long time. This was the unsung prodigy of the Boeing fleet. They didn't expect this aircraft to be a fantastic aircraft when they first got it together, but it became really one of the key aircraft in the entire Boeing fleet. It's used all over the world. And by 2010, this single design of aircraft accounted for 1/3 of all Boeing's profits. So suddenly, you've got Airbus with the A320neo who are about to attack your most profitable aircraft for market share. You have to react. But you've been through 10 years of cost cutting. Cost cutting is the way you do things. That's what your focus is. You've let innovation fall behind. What are you going to do? How are you going to get an aircraft out to the market really fast to compete with this? So what they did was this. They said, right, let's take the 737. It's a great aircraft. And let's stick new engines on it. Let's develop new, much more fuel-efficient engines, put them on the aircraft. We do have to move them forward and pull them up a little bit because they're too big. But if we do this, we suddenly get an aircraft that can compete with the Neo. It's an existing aircraft. We don't have to start from scratch. We can get it out to the market quickly. We can manage costs associated with making it work. And then they had a brainwave. They went, it's practically the same aircraft. More importantly, if we can essentially make it fly the same, we can save a fortune on pilot training. So if the MAX flies exactly the same way as the 737, do the pilots who can already fly the 737 have to do training? And what they basically came up with is no, they don't. So they went out to the market and they said, you have got a team of pilots, and if you go and you buy the Airbus A320neo, it's going to cost you a fortune, but you're going to have to pull those pilots off the line. You're going to have to put them in simulators. You're going to have to buy simulators and loads of simulators. It's going to cost you a fortune. And it does cost a fortune for pilot training. So a very significant cost for airlines. You can do that. Or if you're an existing 737 customer, what you can do is you can buy a 737 MAX, which flies identically to a 737. You don't have to put your pilots in the simulator. We'll give you a short course that you do on an iPad. So this was a massive competitive advantage, and we add more sand to this hill and start to lock ourselves in for Boeing to be able to make this pilot training promise. But they have to make sure that as the development of this aircraft progresses, they don't add any new functionality. That's absolutely critical. The plane must fly the same from the pilot's perspective. They're so confident in it being able to deliver this that they make a promise to Southwest Airlines that if we get this wrong and you do have to do pilot training, we'll give you $1 million per aircraft to cover the training. And with that, development kicks off. And they run into trouble quite quickly. In some of the wind tunnel tests, well, this is where you take your new plane, it's about the size of an American Eagle at this point, you stick it in a wind tunnel and you see how it flies. And they discover a problem. They discover at high speed, tight turns, so we're right at the edge of the envelope now, and flying. But during these high speed, tight turns, this aircraft does this. It's got a nasty habit of kicking up in the air. And the reason it does is because they put bigger engines and moved the position of the engines, they've fundamentally changed the center of gravity of the aircraft. The chief engineer takes a look at this. He goes, okay, it's at the edge of the envelope. It's in high-speed tight turns. This is not something every pilot will have to deal with every day. But it is absolutely conceivably a maneuver they would one day do for evasive action or dealing with turbulence. So we have to look at this. And they look at this and they conclude that this essentially is a stall risk. Remember we said that angle of attack kicks up too far. If it kicks up too far, you lose your aerodynamic ability. You can crash your plane. This could do that. So they have to address it. So they say, right, well, what's the mechanical solution to this problem? How do we deal with it? They looked at putting vanes on the back of the plane. They looked at everything. And eventually the chief engineer concluded the only way to address this problem is we chop off the back of the plane, and we design a whole new tail to deal with the changed center of gravity. Now you can imagine the first meeting with senior executives when you propose that as a solution. It's going to take a long time. It's going to cost a lot of money. And you can be absolutely sure when the FAA hear that we've put a new tail on the plane, they're going to put the pilots in the simulators. There's no way in the world this plane is going to be deemed to handle the same as the old 737 when we've fundamentally changed a key piece of it. So again, we add more sand to this hill where we do not want to put these pilots back in the simulators, and we have to do everything to avoid that. So a mechanical solution is shelved against the wishes of the chief engineer. And instead what they go with is a software solution. And then another reason why engineers shouldn't be allowed to name things is called the Maneuvering Characteristics Augmentation System, which very mercifully gets shortened to MCAS very, very quickly. So what does MCAS do? Well, MCAS is a software system. It sits on the plane and it gets two data sources. It pulls data from one of the two, not both, one of the two angle of attack sensors on the front of the plane. And it also pulls data from an accelerometer on the plane, and it passes them to MCAS. And MCAS monitors the angle of attack and monitors the acceleration, and if it deems that the plane is in this edge of the envelope situation, these high speed tight turns, what MCAS will do is it'll kick in and it will adjust the angle of the horizontal stabilizer in the back, which will pull up the back of the plane, push the nose of the plane down. That takes us away from the stall risk. Seemed like an elegant solution. And then people got really excited in Boeing because it was an incredibly elegant solution, because technically when this is happening, the pilot's not doing it. As far as the pilot's concerned, the functionality and the feel and how the plane flies is exactly the same. It's the software that's dealing with the mechanical difference. So as far as the pilot's concerned, the plane won't kick up because MCAS will stop that happening. Pilot training is no longer required. We don't need to train them with this problem with this aircraft at the end of the envelope because MCAS is going to actually do it. So MCAS is the decision that's taken forward. They go through production of the plane, well, the rest of the design, the production of the plane, they start to sell the plane, airline companies start to fly the plane, use the plane, and we arrive at Sakarya Airport in 2018. We're Lion Air 610. What Captain Sunesia doesn't know is that an angle of attack sensor on the front of his plane had a problem, and the maintenance crew had replaced it. But they'd forgot to align the sensor properly. So even before this plane took off, this sensor was saying that the angle of attack was at a significant angle because of this misalignment. So as far as MCAS was concerned, we're already right up there in terms of angle of attack. The plane takes off, that angle of attack, because of the erroneous measurement, gets too steep. It tells MCAS we got a problem. And the front of the plane starts pushing down. We crash. As we talked about, the public narrative is it's the pilots, it's the air crew. They misaligned the sensor. They didn't deal with the plane properly when they were flying it. The plane keeps flying. Months later, towards the end of 2018, the Indonesian authorities complete their report into the crash. They conclude pilot error, maintenance error. Plane fundamentally okay. Boeing's share price bounces back. We get into early 2019. Share price rises. By March 2019, very beginning of March 2019, the share price is higher than it's ever been inside Boeing. CEO gets a $31 million paycheck. 13 million of that was for performance. And it looked like whatever problem they had with the MAX was over. But only days later, we go to Addis Ababa International Airport. And Ethiopian Airlines Flight 302 takes off. Ethiopian Airlines considered to be one of the best run and safest aircraft in Africa, safest airline in Africa, takes off from Addis Ababa Airport. Suddenly, plane starts kicking its nose down on the pilots, pitching forward. The pilots fight with it, try and pull it back up. Eventually, they lose the battle. The plane hits the ground and physically rips itself apart. 157 people dead in this crash. By this point, the MAX has killed 346 people. Boeing still insists the plane's okay. This was pilot error, would never have happened in America. The FAA insists the plane is okay. Donald Trump insists the plane is fine. So that was obviously very comforting. China moves first and grounds the plane. Australia, Europe pretty much go the day after, ground the MAX. The FAA still argue the plane is fine. It's only when someone on the investigation team brings in one of those traces that we showed of the Lion Air flight bouncing up and down, brings that in along with the newly released Ethiopian Airlines one, and they look at the two of them and you can see that signature pattern of the plane pitching up, pitching down, pitching up, pitching down. And they realize this is not pilot error, this is something fundamental with the plane. And on the 13th of March that year, they ground the fleet in the US. But what had happened? How would you get to a situation, right where we started again, where one sensor can crash a plane? How do you get there? Well, we have to look at the sand pile we've built, which is really centered around MCAS. Once you make that decision that you're going to keep the old plane and you're going to make the old plane work with these new engines and you're not going to have pilot error, and you layer up this hill and MCAS becomes the solution, this end of the envelope thing, you think you're safe. They continue with development and then they get to the flight tests. So this is your first real life plane. Test pilots start taking it up. After 2 months, they come back and say, we got a problem with this plane. That edge of the envelope problem you guys found in the wind tunnel? Well, it turns out that isn't limited to the edge of the envelope in high-speed tight turns. That's something that happens in normal flights at slow speeds. The front of this plane just kicks up. And at these slow speeds, that means it's doing this in takeoff and landing. The time of the flight where the pilots are at their busiest and the most dangerous because you're closest to the ground and you don't have a lot of time to recover if something goes wrong. So suddenly, how do we deal with this? And immediately Boeing get concerned. This is going to absolutely scupper our pilot training plan. We're going to have to put the pilots in the simulators because this plane has a fundamentally different type of behavior during normal operation. There's no way in the world the FAA is going to actually allow us to put this out and just do some training on an iPad if you've flown a 737 before. But then someone has the bright idea inside Boeing. You know, MCAS, why don't we just extend it? Instead of just dealing with this end of the envelope situation, why don't we let MCAS work throughout the flight? Let it stop the front of this plane kicking up. Let it push it back down. Big problem with this was, while MCAS could now still work from that single angle of attack sensor, the accelerometer didn't work at these slow speeds and couldn't be relied upon. So suddenly the functionality of MCAS drops down to reliant on one sensor. And if anything goes wrong with that sensor, you've got a problem. So they basically have their hill built and they're waiting for that one grain of sand of a dodgy sensor to collapse it. And with MCAS extended, they continue with development of the plane. During simulation training, when the Boeing people are using it, they find MCAS is kicking in and out all the time throughout the flight. It's constantly adjusting the angle of the plane. But if you're a pilot and you're stepping on board one of these 737 Maxes with MCAS on board, what does it say in the manual? Absolutely nothing. They never put in the manual about MCAS. You could find it in the index in the back, but that's only because they forgot to delete it out of there. But if you were a pilot, there was nothing in the manual to tell you MCAS was on board. So when Captain Sinasia was holding that trim switch and trying to work out why it felt like someone else was flying his plane, and someone else was flying his plane at this point, and that was MCAS, not only did he not know what to do to deal with MCAS, he didn't even know it was there. Didn't even know it was there. And in that case, your misaligned sensor was sending the erroneous data and it crashed the plane. What was the solution? Remember, this happens towards the end of 2018. It's a long time before we get to the Ethiopian Airlines crash, and the planes are flying in between. Boeing had to come up with a solution. So they said, oh, well, we'll have a software solution soon. But in the short term, here's what you need to do if MCAS goes a bit nuts on you. So this is what pilots have to do. You basically have to hold that trim switch. And what that will do is it'll bring your horizontal stabilizers back up level. Now that's a key step, because by doing that you relieve the aerodynamic forces that are on that horizontal stabilizer. Once you've relieved those forces, you flick these two switches. That cuts the power to the hydraulics that drive the horizontal stabilizer. It doesn't switch MCAS off, but it switches MCAS's ability to actually move the stabilizer off. And then you go manual. You basically manual maneuver this trim wheel here to adjust your angle, your horizontal stabilizer. You got control of the plane again. You can go and land safely. But when you went to the manual and the release and the details for the pilots, it looked kind of like this. And when you get to the second sensor there, or second sentence, which is probably a bit hard to read, it says, electric stabilizer trim can be used to neutralize central control column pitch forces, but more before moving to the stab trim cutoff switches. It doesn't say you must hit that trim switch to relieve those aerodynamic forces. It says you can. And when Ethiopian Airlines Flight 302 takes off, in this case it would turn out there was simply an electrical fault in that angle of attack sensor, that single sensor that was feeding MCAS. Once they got off the ground, MCAS went nuts again. Felt the angle of attack was way too high, kicked in, started to pull the tail up, push the nose down. The pilots knew about MCAS at this stage on this flight, and they knew what to do. They flicked these two switches to cut the power to the horizontal stabilizer. And then when they tried to adjust the trim of it manually, they found they couldn't. They couldn't physically turn that wheel to gain control of the horizontal stabilizer. And the reason they couldn't is they'd missed a step. In the heat of the moment, what seemed fine to execute in a simulator in Boeing would turn out to be complex in a real-life emergency. They forgot to hit the trim switch, and because they didn't hit the trim switch, they didn't relieve the aerodynamic forces on the horizontal stabilizer. So when they manually went to change it, they physically couldn't. They fought with this for a long time, and then in desperation they said, we're going to have to turn the power back on to be able to see what we can do. They flicked the power back on. Of course, MCAS was still getting data saying our angle of attack's too high, push down. The minute the power came back to that horizontal stabilizer, MCAS could control it again, basically put them in a nosedive, killed everyone on board. And this is where we get this disconnect between cause and effect. It wasn't the sensor that crashed the plane. That was just a grain of sand. It was the hill that Boeing had made by its organizational decisions, by its technical decisions, particularly around pilot training, that had produced a hill that all it took was a single sensor to cause an avalanche and crash the planes. And we can go back to the First World War and have a look at it through the eyes of this sort of sandpile model. You know, we talked about the way that it was the assassination of Franz Ferdinand, heir to the Austro-Hungarian Empire, assassinated by Gavrilo Princip, a Serbian nationalist, that started the war. But that's the grain of sand. Let's go look at the hill. And to look at the hill, you have to look at what Europe was at the time. This is Europe. In the middle, you've got the yellow Austro-Hungarian Empire, Germany above it. To the right, you've got Russia. To the left, you've got France, Great Britain up the top, and you've got Belgium tucked in purple in the middle. And you know, the heir to the Austro-Hungarian Empire is assassinated by Gavrilo Princip, who's a Serbian. So things are a little tense between those two countries now. But the Serbs have powerful friends. They know that if they get attacked by Austro-Hungary, they can rely on the Russians to come in and defend them. But the Austro-Hungarian Empire has got strong and powerful friends in Germany. They know that if the Russians attack them, Germany will join in on their side. Of course, the Russians know this. The Russians have been worried about this for years, that Germany's getting militarily very strong. What happens if they get attacked? So what they do is they go and talk to France. They say, we're worried, you're worried. Why don't we make a pact that if Germany attacks one of us, we'll come to the other's defense. We'll make them have a war on two fronts. But of course, Germany knew this. And Germany had a plan as well. And Germany's plan was, it'll take the Russians a long time to get organized. They'll be disorganized. So let's punch through here, beat the French. We'll have the French beaten by the time the Russians are even organized, turn around, go back and beat the Russians. That's the plan. Of course, the French knew that was the plan. So what the French did was they built a line of forts along the blue line to say, all we have to do is slow the Germans down. If we slow them down, give the Russians long enough to mobilize, suddenly Germany's fighting a war on two fronts and we're in a good place. But of course the Germans knew that. They knew that's why the forts were there. And they had a plan. And their plan was called the Schlieffen plan. And their plan was like, let's not do the predictable. Let's just go around them. Go right around the front forts, go through Belgium, down through the north of France where there's no forts at all. We'll be in Paris, beat the French, then turn around, go back, leisurely beat the Russians. We're fine. The problem was Belgium was a neutral country and Great Britain guaranteed its neutrality. So if anyone violated Belgium's neutrality, Great Britain would be forced to come into the war. So what you find is that Europe was in this critical state. And it was in this critical state because of all the interactions and the history that had built it up to that point. It was in such a critical state that all it took was one grain of sand to cause the avalanche. And that one grain of sand was the assassination. But historians now say that it wouldn't have mattered. If it hadn't been that, it would have been something else. It's the shape of the hill that matters, not the grains of sand that fall. And what we find with a lot of organizations is when it comes to safety is that they sabotage safety. They focus on the grains of sand falling and they don't focus on where are the hills inside my organization and how do I deal with those hills to flatten them down a little bit so that it won't take just a grain of sand to actually collapse it in the end. Thank you very much.